All right, get ready because today we are diving headfirst into the truly bizarre world of quantum physics. And our guide on this wild ride is some incredible research from Meta Das. We're going to see how scientists are taking one of the most famous, mind-bending paradoxes in all of science and, just deciding to make it even stranger on purpose.
So, what's weirder than a cat that's both dead and alive at the same time? Well, how about taking that cat and then intentionally making it even weirder? Yeah, that's exactly the wild idea we're digging into. It turns out scientists aren't just content to sit back and observe all this quantum strangeness. They're actively trying to crank it up to 11.
Okay, so our journey has to start with a classic, right? The famous thought experiment, Schrodinger's cat. You probably know the gist of it. A cat's in a box, and until we open it up and look, it's considered both alive and dead. But here's the thing. This isn't just some quirky little story. It's actually a fantastic way to wrap our heads around a fundamental and frankly mind-boggling principle of the quantum world.
So what's really going on here? Well, the key concept behind the whole cat paradox is something called superposition. And what that means is a quantum system can be in multiple, totally contradictory states all at the same time. Think of it like a light switch that's both on and off simultaneously. It makes no sense, right? For our poor cat, it's being both dead and alive. This is exactly what we mean when we say non-classical. It's behavior that it completely breaks the rules of our normal everyday world.
Okay, but wait, how in the world do you see something that's in two states at once? You can't just snap a picture of it, right? To actually visualize this, scientists needed a really special tool, something that could create a map of a system's quantumness. And that tool has a name, the Wigner function. Now, the best way to get your head around this is to think of it like a machine that spits out a 3D topographical map of a quantum state. It's like a landscape, and the shape of that landscape, the hills and valleys, tells us everything we need to know. It shows us if the system is behaving normally, classically, or if it's doing something truly deeply weird and quantum.
So what does a normal map even look like? Well, here you go. This is it. This is the Wigner function for what's called a coherent state, which is basically the closest a quantum system ever gets to behaving like a normal object in our world. And notice how it looks. It's just a single, smooth hill. Everything is positive. There are no weird dips, no strange valleys. This is our baseline. This is what not weird looks like in the quantum realm.
Okay, so if that smooth hill is normal, then what in the world does the map for our Schrodinger's cat, a system that's in two states at once, actually look like? Let's see it.
And this is our quantum cat. Whoa. So right away, you can see two different peaks, right? Those represent the alive and the dead states. But the most important part, the real magic, is what's happening right there, in between them. You see those ripples? Those valleys that actually dip down into negative territory? That is the visual signature of quantum weirdness. It's something called quantum interference. And those negative values, they're the dead giveaway. It's kind of like finding a place with negative probability, which is something that just flat out cannot happen in our classical world.
And this right here perfectly illustrates the core idea of this whole research project. As Meta Das puts it in her abstract, those negative dips in the map, they're not just some weird graphical glitch. Nope, they are a direct measurement of how non-classical or how purely quantum a state really is. It's simple. The deeper the valley, the weirder the state.
Okay, so now that we have a way to actually measure this weirdness, we can ask a really fascinating question. Can we take this already super strange quantum state and deliberately make it even weirder?
And that brings us to the central experiment of this whole dissertation. The goal was to find out what would happen to the quantum nature of this cat state if you deliberately punched it by adding photons. Those are the individual particles of light.
And the results are, they're just remarkable. Have a look. On the left, that's our original cat state, right? On the right is what happens after you add just one single photon. Look at that valley in the middle. It's instantly deeper, it's more complex. The quantumness of the whole state has been amplified just like that.
And believe me, it gets even more extreme. This is the result after adding 10 photons. The change is just stunning. That negative region has totally transformed into this vast, deep chasm with these incredibly intricate patterns. The state didn't just get a little more quantum, it got completely supercharged into something way more bizarre and non-classical than it was before.
This is all visually stunning, right? But it brings us to the most important question of all. So what? Why would scientists want to make something weirder? Why is more quantum actually better?
Well, the answer is that all this weirdness, all these non-classical properties, this is the very engine that's going to power future technologies. Being able to create and control these highly quantum states is a non-negotiable step towards building more powerful quantum computers, creating communication networks that are fundamentally unhackable, and making sensors with a precision we can barely even imagine.
Let's just take quantum computing, for instance. Your computer, my computer, they run on classical bits. And a bit is simple. It's either a 0 or a 1. That's it. But a quantum bit, a qubit, can be a 0 and a 1 at the exact same time, all thanks to that superposition we were talking about. And what does that mean? It means a quantum computer can explore tons of possible solutions to a problem all at once, giving it this absolutely massive advantage for certain kinds of problems.
And really, that's the big takeaway here. The work we've just seen, this proof that we can take a quantum state and intentionally crank up its quantumness, it's not just some abstract theoretical exercise. It's a fundamental step. It's about learning to master the actual building blocks of technologies that could, and probably will, completely change our world one day. Which leaves us with a pretty mind-bending thought to wrap up with. We've just seen that the fundamental strangeness of reality isn't just a fixed thing. It can be intentionally amplified. So if we can do that, what else is possible? What other fundamental rules of our universe are just sitting there, waiting for us to figure out how to bend them?